Hey, hello everybody, Mr. Mark with you, and today we are looking at Skill 2.d for all AP Physics courses. Specifically today I'm focusing on Physics 1, but the content applies to all of the different physics courses, Physics 2, Physics C, and Physics C, E, and M. So I noticed that my Physics 1 students this year were not doing so well with these sorts of questions, so I'm taking a little bit of time to just go through and review what these things look like and some of the strategies. This screenshot comes from the AP Physics 1 course and exam description, which is basically the book that tells physics teachers what to teach in their AP courses. Practice 2, Science Practice 2, is mathematical routines, and Skill 2.d is predict new values or factors of change of quantities using functional dependence between the variables. So we're going to kind of unpack that and see what that means, and then we're going to look at some examples and some strategies. So predict new values might look like something like this. Suppose you have car A that travels 40 meters in 10 seconds, and then car B travels the same 40 meters, but it goes twice the speed of car A. So the question is, what is the time that car B takes to travel 40 meters? So that's predicting a new value. We change something, how do we get the new value? Kind of another way to phrase a question like that would be a factor of change. So suppose car A1 has speed V1, and we know that car B has speed 2V1, it's like twice the speed. We could ask questions like, what is TB in terms of TA, or what's the ratio between the two, TB over TA? So those are very common ways where you might see this sort of thinking. And so there's a couple of different ways you can approach these sorts of things. Kind of conceptually, you can say, well, if you double the speed, you would have the time needed to go a set distance. A lot of people can do that sort of stuff without thinking about it too hard or really even writing down an equation. The thing is, though, you don't have to do it in your head. You can use an equation, use physics, just like if I were to say, calculate the time car B takes to travel 40 meters, you can do the same sorts of physics equation things, just using ratios and substituting in new values. That's what we're going to work on. So that might look like, I know velocity is change in position over change in time. So if I double the velocity, in order for the equation to still be true, like the left side equals the right side, I would have to halve the time. Otherwise, the equation would no longer be balanced. You could do something like plug in numbers. If I put in 2v on the left side, the only way the equation becomes balanced is if I put in half delta t on the right side. So those are the sorts of strategies that we're going to investigate. So the first thing that you still have to do is identify the pertinent physics. So a lot of situations, if I were to say to you, calculate how far car B travels, and here's its displacement in time, you would go, oh, v equals delta x over delta t, and I can solve for how long it takes. Start with the same physics point. You're just going to manipulate it in a slightly different way. So let's look at an example. And again, this comes from the course and exam description. This is a public document. This isn't anything secret. It's on the interwebs. It's on College Board's AP Central site. So we have this rock sitting at the bottom of a cup filled with water. And the upward force exerted by the water is F0. We then replace the water by it with an oil that is 3/4 as dense as water, and then we again put the rock at the bottom, and the question is, what is the new upward force? And it's not just calculate what it is in newtons, it's give it to me in terms of the original force F0. So the first thing that we have to do is identify the pertinent physics. So the upward force is a buoyant force. So we need to remember what causes buoyant forces and how do they work, what factors affect them. And so we have the density of the fluid, the submerged volume, and G. There's no indication that we've moved to a different planet, so G is not going to change. And then there's no indication that the submerged volume has changed. Like, in fact, we're told that the rock sits at the bottom of the cup, completely under the oil. So the two things that I'm looking at here are the force, the buoyant force, F0 in this case, and the density of the fluid. That's the thing that's being changed. So the next question is, how does the changed variable affect the other variable? So if we were to replace the original buoyant force, the original density with 3/4 the original density, what would we have to do to the left side to make the equation still be true? And the answer is, well, since rho is in the numerator, it's not being divided or anything like that, then I just need to put a 3/4 on the other side of the equation in order to make the equation still be true. So the density of the oil is directly related to the buoyant force. So if I increase the density of the oil by 3/4, I would experience, a increase in the buoyant force by 3/4. So this new oil would exert a force of 3/4 F naught. Now the next one, maybe not the next one, but a following one, we're going to look at eliminating answer choices. And you could have probably done all that, or gotten the correct answer without having to do all that, because if the fluid is less dense, it's not going to exert as large a buoyant force. And so A is the only one that has a buoyant force that is less than F naught. So we're going to look at, I think, the next example and see how we can use that to prevent math mistakes that we might make. Speaking of the next example, this one also comes from that public document, the course and exam description. And in this question, you have two disks that are experiencing an external torque over the 5-second time interval of the graph. We're told that disk B has a rotational inertia that is twice that of disk A. And then we're told, oh, no, sorry, that doesn't matter. We're told that the magnitudes of the net torque on the disk from that time are tau A and tau B, and we're supposed to come up with a relationship that relates tau A and tau B, more specifically tau B in terms of tau A. So the first thing that I did with that is said, well, if I want averages, maybe I should just go ahead and draw like a single line to represent the torque from 0 to 5, and that would give me the average. Then I need the pertinent physics again. And so impulse momentum for something rotating, the change in angular momentum is the torque times the change in time. I got to do a little bit of rearranging here because I'm interested in torques. So if we rearrange that and we get torque equals delta L over delta T, well, that's just the slope of that graph. And so the physics tells me what to look for. Now I can do a mathematical comparison. I can just look at the graph and tell that the slope for B is twice as large as it is for A. It may not always be as simple. So you may at this point have actually needed to calculate the slope in order to make that comparison. Unfortunately, there's one that says tau B is twice tau A. Notice that in this question there's some unneeded information about the rotational inertia being larger. That would affect their angular accelerations, but it doesn't affect the torques involved. And this question is about the torques, not the net effect or the net acceleration. Okay, so here's another example, again, from the course and exam description. It's available on the internet, where you have a fluid flowing through a pipe. And it goes through a narrow section, and then it goes through a wide section. And we're supposed to get the ratio of the velocities in the wide section compared to the narrow section. So again, this would be a 2D functional dependence type question. Step one is still identify the pertinent physics. And so here I need to use the equation of continuity to relate the velocity in the narrow section to the wide section. So A1V1 equals A2V2. The thing that's changing is the radius of the pipe. So at some point I need to relate that to the area of the pipe. The fluid is going to slow down when it gets to a wider section. So as the area gets bigger, the fluid is going to go slower. So V wide has to be less than V narrow. So what I'm going to do, kind of sneaking a peek at the answers I'm given, is try to eliminate at least half of them, because two of them have a ratio greater than 1 and the other two have a ratio less than 1. So I should be able to eliminate half of them if I can just figure out should that ratio be bigger or smaller than 1. So since the question asked me to do V wide over V narrow, and V wide has to be smaller, I'm going to go ahead and eliminate C and D. I don't want to accidentally make a math mistake and get the inverse of the ratio I'm looking for, which is really easy to do on a time test. And then come over there and go, oh, that answer's sitting there in front of me, that must be it. Eliminate the unreasonable ones before you start doing all the math tricks that we're doing. Okay, I'm just going to rewrite that in terms of narrow and wide so I don't lose track of which one is 1 and 2. And then I'm just going to solve for the ratio that I'm being asked to solve for. So in this case, it's VW over VN. Move everything else over to the left side, or excuse me, the right side of the equation. So AN over AW on the other side. And then the area, since it's a cylinder, would just be pi r squared. And all I have to do next is put in the radii that I'm given. So on top would be r for the narrow section, 2r in the denominator for the wide section. And common mistake here, like put parentheses around those radii. R and 2r are the radii. You need to square that too. And so r squared over parentheses 2r squared would be r squared over 4r squared. And then the r squares would cancel and you would get a ratio of 1 to 4. So on this one, we would go with A. So be careful about things like plugging in a value for another value. We're comparing things here. It's important to compare them correctly. So when you're plugging in that radius, be sure you square that radius, the whole part of it. Like it's 2r squared to give you 4r squared over there on the right side. So this skill doesn't just show up on multiple choice questions, it also shows up on free response questions. Most specifically, the experimental design question, which will be number 3 on your AP Physics exam, in the parts where it asks you, what do I graph? So figuring out what to graph is the same skill. Like how does variable A relate to variable B? And then how do I make that into a thing where they're going to be direct proportional to each other so I can get them to make a straight line. And so this question, again, is taken from the course and exam description, the publicly available, nothing secret here. And it asks students to take data of height and speed. So we're launching something upwards with some speed and figuring out how high it goes, and generate a straight line graph that can be used to find the acceleration due to gravity, so G. In Physics 1, the examples that we've seen, they've given one of the axis, and the student is asked to figure out the other one, and they're also given an equation. In Physics 2, C, and E, and M, that's not the case. So you gotta figure out what the pertinent physics is in those courses. But here, we're kind of given the starting point. Like the students derive that the relationship between H and V is given by V equals square root 2GH. So your job now is to basically make that look like y equals mx plus b. Because if it's y equals mx plus b, then it must be the line that'll fit on a graph. And so we're already told that the vertical axis will be v squared. So let's take our equation and make it look like the one that we're going to have to graph. And so instead of v equals, I'm going to write v squared equals, and then go ahead and square everything on the other side, which works out nicely. It's just 2g times h. So speed is one of the variables. That's the one that I'm putting on the vertical axis, speed squared actually. The other thing that's changing is the height. So now we have to identify what's changing and then find where that is in the equation. If the variables aren't already on opposite sides, it's really important, we do a little bit of algebra to get them on opposite sides because I need one variable on the left and one variable on the right. So that's already done. V is on the left, H is on the right. Since V is by itself, let's make that the y-axis. If V wasn't by itself, since I'm told to make that the y-axis in this case, I would move anything that V is being multiplied or divided by to the other side. It would just become part of the term with the h in it. H is the other variable. It's got other things with it, so we're going to make it the x. And then all those things that are multiplied or divided would be the slope of the line. So in this case, the slope of the line is going to be equal to 2 times g. So in order to graph this, we'll graph v squared versus h. We'll find the slope of the best fit line. And then in part D, we'll use that slope to figure out the acceleration due to gravity. So basically divide the slope by 2 to get g. Now, there are other ways to do it for this particular data set. And if this was a Physics 2 question or a Physics C question, you would have to decide both axes. Physics 1, it seems like they're going to give you one of them. You just have to make what you're going to do fit that. So if you're thinking, oh, I'd graph v versus the square root of h, it would work, but it doesn't answer the question that's being asked. So make sure that you answer the question that's being asked if you're in Physics 1. The first part of this question, kind of backtracking here, was students are given a cylinder and they're supposed to figure out the density of the liquid in that cylinder. And so again, start with the pertinent physics. In this case, you have to start by writing the experimental procedure out. So we've got to kind of figure out, well, what do we have that's going to be able to measure the density of a liquid? So I've got meter sticks and I've got pressure sensors. So that tells me that I can do pressure equals rho GH. So I can measure P and I can measure H, and then the density can be found somehow, we'll figure that out here in a bit, from those two measurements. So kind of recognizing that H has stuff multiplied by it, I should make that the horizontal axis. P is over there by itself, I should make that the vertical axis. Then rho times G would be the slope of that best fit line. So I'm going to answer part B to this question first, which I think is probably a good strategy in general. I'm somehow going to get pressure and put that on the vertical axis. I'm going to get heights with my meter stick, put that on the horizontal axis, get the slope of the best fit line, and then divide that by G to get the density. Then I can work backwards to part A and talk about how I'm actually going to do that. Put the pressure sensor in there and measure how deep it is, measure the pressure from the sensor, and then move the sensor to different depths and repeat until we're tired. It's time to go home. So in the first part of a lab-based question, it's probably a good idea to do part B first. That way you can know what you're shooting for as you start working through part A. So part A is really just describing the measurements you're going to need to do in order to make B happen. And then one other question, and this is a very common physics question. It's just one from my oscillations unit. Students like you are given a pendulum, which you have connected to a string and you let it oscillate. You have access to a meter stick and a timer, and that's it. So you don't have a scale or anything. And again, we're going to measure G. That's the goal here. And so you still start with what is the pertinent physics. And in this particular case, since you have a timer and you have a meter stick, I would think that the pertinent physics would be the period of a pendulum equation. So T equals 2 pi square root L over G. I can use my timer to get the period. I can use my meter stick to get the length, L in the equation. Since G is in there, but there's also some other things, I'm going to group all of those things that aren't the highlighted variables together and kind of rewrite them like that. So G is what I'm after, but there's also the 2 pi part. So I'm going to rewrite that like T equals all that stuff in parentheses times the square root of L. So now I can go, T is going to be my vertical axis, square root L will be my horizontal axis, and the stuff that's in parentheses, 2 pi over the square root of G, would be the slope of the best fit line. So to get G, do a little bit of algebra real quick, just take 2 pi over the slope and square it to get G. So these are some things that can be practiced. I think most of the time it's recognizing that we can still use equations to answer these sorts of questions to figure out what's happening, even if we're not directly solving for something. Like we're not solving for T or G in this case. We're being asked how would you graph it in order to get G from the slope. I hope this has been helpful. Till next time, ta-ta.